By just acknowledging some of my collaborators from Sheffield, particularly Mark Strong, Richard Wilkinson and Jeremy Oakley, who've been very helpful over the last few years in enabling me as a kind of engineer and cardiac modeler to understand some of the statistics that is important when we start thinking about uncertainty quantification and sensitivity analysis. So I think part of the background to this talk and part of the background to the program that we've been running over the last 3 weeks here is to do with models and some of the problems that they present us with. And I was here in January last year for another workshop, and a number of the statistical people there quoted this guy Harlow Shapley, who's an American astrophysicist. And this quote really struck me because in the cardiac modeling community, there's another guy called Alan Garfinkel from California who is fond of saying exactly the opposite. Okay, so Harlow Shapley is skeptical about models and less so about observations, whereas Alan Garfinkel highlights the opposite. And this feeds into some of the conversations about trustworthiness and confidence and uncertainty that underlies what we're here for. Because we've seen already that cardiac modeling is become well established as a research tool, and it's making the transition towards the clinical setting and for other applications, which, as Gary said in the introduction to today, are safety critical applications. So this raises the question about how we handle uncertainty and variability, how we know models are trustworthy for particular applications. So this is one of my lists of uncertainties in cardiac models. It's not exhaustive, but it highlights some of the issues that there are. And there's a couple of review papers which unpick some of these sources of uncertainty, some of these considerations in more detail, which are worth looking at if you're interested in this area. But one of the things that comes out of beginning to think about this is that useful models need to strike a balance between complexity and uncertainty, because the more complex a model, the more parameters you have, the more uncertainties you're likely to have built into the model, either within the parameters or the assumptions that underlie the different model components. So taking these kind of things into account, we've started to think in our community a little bit about sensitivity analysis and uncertainty analysis. And we can define these in different ways, but for the purposes of this talk, I'm going to consider sensitivity analysis to be about the way that different inputs or parameters, so I'm going to talk about inputs rather than parameters, how they contribute to the model output. And these can give us insights into how the model works. That's particularly important for cardiac cell models where that may not be at all obvious. And also to identify those model inputs that if we can pin those down to reduce the uncertainty in them, then we get a lower output uncertainty. And uncertainty analysis is related. It's not a separate topic, and it's about thinking through sensitivity analysis in terms of uncertainties. So being able to quantify how uncertain a model output is if you've got uncertain model inputs. And as we begin to do these things with cardiac models, then as we've seen in some of the presentations today, hopefully we'll be able to work towards more probabilistic workflows. So what does that look like? Well, if we have our computational model, which could be a cardiac cell model, could be a full-blown multi-scale whole organ model, there are going to be a number of parameters and inputs, and typically we take those to be a fixed value at the moment, even though there's not really a good reason for doing that, because many of the parameters in our models are not physical constants. They're likely to vary. So we take an input and another input, and instead of taking these as fixed values, we take these as a random number with a distribution, and then we have a distribution on our output. And what we have here is two distributions on each input. We've got a blue one and a red one, where here we've made the size of the distribution, the width of the distribution a bit bigger, and we've made the width of this distribution a bit bigger. And that might have a different influence on the model output. So here, the red distribution, so that's input 1 here. We've increased its width, the width of the distribution. Here we've not changed the mean of our output, but we've changed the distribution slightly. But here, we've changed the width of the distribution, and because of something that's going on in the model, we've actually changed the way the output looks, the mean of the output. So how can we get towards this? How can we generate distributions on the model output? Well, one thing that can be done is to run the model lots of times. So we sample from our input distributions, run the model, and then repeat until we build up a distribution on our outputs. What I'm going to talk about is replacing the mechanistic model, or the mathematical computational model, with something else that is able to reproduce outputs more quickly. And sometimes these are called surrogate models, or a response function, or a meta model. Now, the emulator can be used to generate Monte Carlo distributions. You can run it a lot of times. But I'm going to talk about a particular type of emulator where we can handle uncertainties, or handle the uncertainties on the inputs explicitly without having to do Monte Carlo. So to help us think about that, it's useful to think about what our models are. And generally, we've got a number of inputs to our model, which I've labeled X in this particular notation, and a number of outputs. So we can actually think about our model as just a function. So the outputs are simply a function of the inputs. And that's quite helpful, because then we can say that our emulator is another function, here f prime in red, which approximates the behavior of the model when it's presented with the same set of inputs. So the idea is that we take our model, we replace it with something else that has the same association between, or approximates the association between inputs and outputs. And the great thing about our emulator, especially if it's fast running, is that we can predict our model output for new inputs. And I've just shown these in blue here. The type of emulators that I'm going to talk about in this presentation, and I'm going to go through a worked example with a particular cardiac cell model, is a Gaussian process. And before I talk about Gaussian process emulators, I should say it's not the only way to do this. There are lots of ways of emulating a model. It's one way, and one of my concluding remarks is going to be that we don't know what the relative merits of these different approaches are at the moment. It remains a bit of an open question. But a Gaussian process is a statistical model that is a distribution over functions, so we can draw functions from it. And what it effectively does is to interpolate an output surface. And once we've obtained a GP, and I'll explain how that happens in a minute, we can use it to calculate the expectation on the output, and also the variance on the output for any new set of inputs. So that's the interpolation part. The GP has a number of hyperparameters which are fitted using a set of design data. So this involves running our computational model for a number of times to get a load of different outputs corresponding to inputs. And we use that set of design data to train the Gaussian process. There are no particular assumptions in this process, except that the output of our model is smooth. And the great thing about having an emulator like this is it's very, very fast. I'm not going to talk about this today, but it does mean that we can explore the input space, which might be very high dimensional for a cardiac model, quite thoroughly. What is important for what I'll say today is that we can specify any of our inputs to be uncertain, so we can specify means and variances for our input parameters. And if we make the assumption that our inputs and outputs are normally distributed, then we can calculate the distributions on outputs directly. And that's going to come in handy as well. So I said there'd be a worked example, so I'm going to talk about the Courtemanche-Ramirez-Natel model for the human atrial action potential. So I guess most people here will have seen diagrams like this. There have been a few already today. But this is a diagrammatic representation of the cell with a membrane and ion channels, pumps and exchangers embedded inside it. Now we need to think about what model parameters to look at, what we want to emulate, and what we've done in this study is to look at the maximal conductances of the ion channels. So there are 9 of them in this model. We've looked at 3 pump exchanger maxima, 4 external boundary conditions, so that's the membrane capacitance and extracellular concentrations of sodium, potassium and calcium, and 4 of the parameters related to calcium handling inside the model. What we haven't done, as Prof did in his model that he described this morning, is to look at the dynamic parameters, so the opening and closing parameters of the ion channels. We've just looked at the maximal conductances. So those are our X's, those are our inputs for this particular worked example. For the outputs, we've picked a number of quantities that came to capture the shape of the action potential. So we've got action potential duration at 50% and 90% of repolarization, resting potential, action potential amplitude, maximum upstroke, and a number of measurements of the voltage during the time course of the action potential. And a minimum and maximum for the calcium transient as well. So that's a list of 20 inputs and 11 outputs that we wanted to look at. So to train the Gaussian processes, we had a separate emulator for each output. It is possible to have multi-output Gaussian processes, but this kept it simple, especially for me. That was helpful. We implemented the Courtemanche model using code generated from CellML. We ran the model 300 times. Happy to discuss whether this is enough or not. It's a bit of an open question, I think, as to how many times we need to run the model. Some people talk about a rule of thumb as 10 times the number of inputs. So we did 10 times the number of inputs and then a few extra to be safe or to overfit, depending on your perspective. We varied our inputs plus or minus 50%, except for GK1 and the membrane capacitance and ion concentrations, which have a slightly smaller variability. Now again, it's something that Pras mentioned this morning. We had a number of, 5 out of our 300 runs where there was some kind of odd behavior. So there was pacemaking or APD alternans or other problems. We removed those. And we also ran our model, the cell model, another 150 times to compare the output from the emulator with the output from the cell model. And we did that using the mean average percentage error, which was generally less than 10%. So we were fairly confident that our emulators were doing okay. So this is possibly a bewildering slide. Don't concentrate on individual points, but this is a snapshot of our design data with each of our inputs, each of the 20 inputs along the bottom, and each of the outputs is a row. So some of these, so maximum sodium conductance and maximum dVdt, are quite well correlated, as we would probably expect from knowing how the model works. But for a lot of these intersections, there's no obvious relationship. So when we built our emulators and we do some additional calculations, we can calculate variance-based sensitivity indices. So what these are, and I'll come to the details here in a moment, these are the proportion, if we make our inputs uncertain, they are the proportion of the output variance that is accounted for by each uncertain input. And we can directly calculate these proportions. To do this, we set our inputs to have their default value for the model and with a particular standard deviation or particular uncertainty. And again, here we've got a grid with our outputs are rows and our inputs are columns. And I've assigned a number where the sensitivity analysis was greater than 0.05 or 5%. And where the squares are blank, then these numbers were small. So there's a few things that kind of stand out from here. First of all, there's these numbers on the right-hand side. So these are the sum across the row. Now, because each of these sensitivity indices is a proportion of the total output variance accounted for by each input, these should sum to 1 unless there are interactions going on among the different inputs. So by and large, these are quite close to 1, although for APD50 it's 0.86. So that's suggesting there is some interaction going on. I've already highlighted that dV/dt max, so the upstroke of the action potential, strongly correlates with sodium conductance, and that is reflected in a large sensitivity index. Also, some of the inputs have quite a strong influence on a number of the different outputs, and that's the L-type maximum conductance of the L-type calcium channel that I've highlighted. And also some of the outputs I've highlighted here, APD90, are influenced by a large number a relatively large number of the inputs as well. So I've explained that these numbers are proportions. You might be wondering why some of them are positive and some of them are negative. So what I've done there is to look at another thing that we can calculate directly from our Gaussian process, which is the main effect of each input on each output. And I'm not going to go through the main effects for each output, because that at 4 o'clock in the afternoon that might be quite hard work for everybody. But just as an illustrative example, these are the main effects for APD90. And each line here represents a different input here. And these essentially show how how this particular output changes as we vary each input across its range, which is mostly plus or minus 50% of the default value, while averaging over all the other uncertain inputs. And so the signs here on this sensitivity analysis plot were calculated from the gradients of these main effects. And that gives us a sense that the inward currents, like the calcium current, tends to work in an opposite way to an outward current like the ultra-rapid potassium current. So we've got a red column here relating to the measures of the action potential plateau and early repolarization, and a blue column here. And the other point to make from these this example main effects plot is that some of these main effects are quite nonlinear as well. So some of them look reasonably linear, but there's some nonlinearity going on there as well. So the final thing that we can do is to think about the uncertainties in our output. Again, this is an example for APD90. And what we've done for these graphs, so the x-axis in both cases is the standard deviation that we've assigned to all of our inputs to start with. and the y-axis is the coefficient of variation. So that's the standard deviation divided by the mean. So it gives you a sense of how big, how much the standard deviation on the output is changing as we increase the standard deviation on the inputs. The 3 lines here just show this relationship with different means, but essentially they're getting bigger, and we've got a coefficient of variation of up to 15% on our model output. So what we've done here is to make some of our inputs certain and some of them uncertain. So we're looking at how we can reduce the uncertainty in the output if we know some of our inputs more precisely. So the red line here corresponds to the red line here, and the purple line and the green line correspond to what happens when we fix some of our inputs and we reduce the uncertainty. So, that's kind of intended as a worked example of how you can use these tools to analyse a particular cardiac cell model. To finish off, I have some remarks. And the first thing, and for those of you who are here for the workshop, for the rest of the week, you may hear this kind of sentiment expressed quite strongly again. If we're modelling, particularly for safety critical applications, we really do need to account for uncertainty and variability much more carefully than we do at the moment. And as I hope I've shown that Gaussian processes are a potentially useful tool in this regard, but as I mentioned earlier, it's not clear what approaches work best yet. This whole topic is really interesting, well, interesting to me at any rate, but I think if you're an early career researcher looking for something to get interested in, you can choose something more boring, but it would be a really good choice to get interested in this area because it's really important for pushing our field forward. And if you want to have a go with some of the tools that I've talked about, my postdoc Sam Coveney, who will be here tomorrow at Thursday and Friday, he has a Python implementation which is available from GitHub under a standard GPL license for anybody to play with. Thank you very much.
Any questions? Good.
Richard, your sensitivity analysis, you mentioned that in the cases where it didn't add up to 1, there was some, I can't remember the term you used, but in my mind there's some compensation, I guess, between some components where maybe...
Interactions. And
so did you, in fact, look to see specifically in those cases which components of this particular model were interacting or compensating for one another? Is that the right way to think about it?
And the answer is no, but we should. We've recently put that functionality into the code. So, but yes, it would be really interesting to know which, because essentially there's some variance which is accounted for by an interaction between between two of the inputs. At least that's how I understand it, and other people who understand the statistical foundations better will be able to explain it more clearly. But it's a useful diagnostic, I think, for that kind of sensitivity analysis.
Yeah. So obviously I agree with much of this. Okay. Terrific.
Good.
Now one point though, because you talk about the uncertainty analysis as going from the input uncertainty to the output uncertainty. But of course the real uncertainty analysis goes from the model to the real world. So there is a gap here. For example, when you listed all the uncertainties on an early slide, the fundamental question about how does the model represent the world, which is possibly the biggest uncertainty, actually wasn't on it. So it was surrogates' fault were, but all of those uncertainties could be small, but the model could just not represent the world at all. So my fundamental question is that where do you think uncertainty analysis really is? I mean, well, this is a key component. Until you can understand how the model works, you can't understand what it says about the world. But there is still like a huge gap.
Absolutely, I'd agree. And this is a very model-focused talk, so which is why I didn't touch on that. But I think it's a really important consideration. Somebody, I think it was probably Gary, mentioned model selection this morning. So this is one cardiac cell among many, and the extent to which it fits or not with the real world, or how far it deviates from the real world, is an important consideration for model selection. So,
because it even changes the way you frame a lot of your questions. Because one of the things you said, for example, was that if you put in too many parameters, so the whole thing becomes out of control and model uncertainty grows. The model uncertainty might grow, but your real world uncertainty might reduce. These parameters might be explanatory, which would therefore be relevant to the real world reactions. So that what makes a good uncertainty analysis for a model might not be the right uncertainty analysis to do if you want to carry it forward.
Yeah, no, that's really helpful.
The field of imaging and image analysis and computational modeling is being steamrolled by deep learning. And, I'm just wondering, the philosophy there is that you have millions of parameters, and you are performing lots of tricks to try and make your model robust. The advantage of this one seemed to be that you could compute the variance in the output directly, but you can also do that numerically, right? So
Yeah.
do you have any comment about the philosophy of these approaches? So what I mean is that I think we're going to see in the next year or two a lot of very highly parameterized models in this space.
Yeah, I mean, it's. I mean, Gaussian processes. Some people would say that they're useful for statistical machine learning and classification and that sort of thing. So they're kind of part of that technology, but not really AI. So I don't know if that answers your question, but it's useful.
Maybe over a beer.
Sorry?
Maybe over a beer.
That sounds good.
We'll move on unless there's anything pressing. Okay. Thanks very much, Richard.
Okay.